As we have discussed in the previous lecture, as we have concluded in the previous lecture, so 4 quantum numbers in some sense completely defined the electron structure of each element, of all elements in the periodic table. And again, in some sense, this electron structure defines or predict, if you wish, the type of bonding which we can expect when we manufacture, fabricate some special materials. And based on that, so the 3 main, if you want, type of atomic bondings were outlined, among them ionic, metallic, and covalent. And also we mentioned the weak bonding, so-called van der Waals kind of bonding, which plays an important role, for example, for polymers. But in any case, so we decided that this type of bonding, they in turn define the different material properties. So it means that some material properties, including mechanical properties and physical properties, are defined by this level of material structure. So on this lecture, let us consider several special examples of the mechanical and physical properties of the material, and I will try to explain you, to give you some, if you wish, qualitative sense how atomic level, atomic scale of material structure defines this kind of properties. So these properties is better to explain with the help of so-called, let's say, force atomic distance or energy atomic distance diagrams. So what does this diagram mean? So on this screen, you can see the force distance and energy distance diagram for 2 atoms. Let's consider the ionic type of bonding, let's say, between 2 atoms now. One atom has its own electron structure, the other atoms, the other one. You remember that ionic bondings typically occurs when we do have so one atom with, let's say, 1 or 2 valence electrons, and the other atoms 7, 6 valence electrons. In this case, they easily interchange with electrons, and we do have positively and negatively charged ions, and there is an interaction, very well known Coulomb interaction between these 2 atoms will start its work. So assume that we have these 2 atoms, and so at the beginning they are on the very long infinite distance between each other. So no any force in this case almost occur. Also, in some sense, the energy of this system is equal to 0. However, you know, because we do have the Coulomb force, in the Coulomb force, the attracting force is inverse proportional to the square root of the distance between 2 atoms. When we start to decrease distance, this attracting force starts to play its role, and so if there is no any other force, at some point these 2 ions should collapse. So you know from your experience that it's never happened, just for the reason that at some point, so the other, in this case, repulsive force starts its work. And the nature of the repulsive force is relatively straightforward in the case of the ionic bonding. So we do have the overlapping of the electron, if you will, shells of the 2 atoms. And both the shells, they have the negative charge. It means in this case we do have indeed repulsive force. In the case of the repulsive force, the dependence is of this force as a function of the distance is inversely proportional to the 8 or the 9 even power of the distance. So it means that it starts play its roles when the distance between 2 atoms very small, however they are very strong. So now we do have two forces, attractive and repulsive. For sure, we can imagine that at some point, so the net force in this system should be equal to 0. And in this case, we do have, in some sense, the equilibrium condition when there is no any force acts to positively charged and negatively charged ions. And so we do have the stable case for our now fabricated material, if you wish. So, and you can see on this slide that, so this corresponds to some R0 distance between these two charged ions, between these two charged ions. So the same interpretation can be presented if we use the term energy, not force. You can imagine that, so at equilibrium, so the total energy of the system should be equal to its minimum, and you can easily see that indeed at the distance r equals r0, when the net force between the two charged elements, two charged atoms equals to 0, we do have the minimum of energy of the system. And actually this minimum of energy is defines the whatever property we will talk later today. And so it's correspond to some value, specific value for different materials. This value is different. We use letter U0 to define this energy. So U0 plays very important role in future, will play a very important role in future in our explanation on the relation between the atomic level of structure and mechanical, for example, or physical properties. So let's take one example now. So if we feel ourselves comfortable to understand this kind of dependencies, energy distance or force distance dependencies, now we can just move and pick up one property. So here, which is so-called elastic modulus. We will talk about just refresh our mind a little bit, and to talk about the elastic deformation. You know that you have your material, and then you apply, for example, load to your material. You will stretch the bonds, as you can imagine, but we will apply not so large load. We will apply it in the range of loads when, so we unload our system should return to exactly its initial position. So in this case, we are talking about elastic deformation, which means elastic means reversible. So that's, we refresh our mind a little bit about the elastic deformation. Now we can come to the picture of the atomic bond. So we have two atoms here in equilibrium, so there is a distance r0 between them. Then we start to apply load, or this load F between these two atoms. So the distance between two atoms increases, let's say on some delta R. And so there is a relation, very well known relation between the applied load and the change of our sample, let's say, length. So so-called Hooke laws, and it's a linear relation between the applied stress and strain. And the coefficient of proportionality, E here, as you can see on this screen, is so-called Young modulus or elastic modulus of material, which typically is measured in the gigapascal. So again, coming back to our atomic picture, to the energy distance diagram. And so on one hand, it's straightforward based on the common sense. So larger U0, larger U0 do we have, the highest elastic modulus we have to expect in this system. But frankly speaking, this relation is not so straightforward. There is no straight proportionality between the elastic modulus and so U0 in this system. So now, in order to understand the real relation between the elastic modulus and atomic level of structure, we have to come back to the force distance diagram. And on this screen, you can see this kind of diagram for two different materials: the weaker material, the lower one, and the stronger material, the upper one. If you remember, the intersection between these curves and the x-axis correspond to the equilibrium distance between the atoms in this material to R0. So now when we start to apply the load, so you will see that the stiffness of the bond will be proportional to the derivatives of the force at the point R equals R0. Larger the derivatives, so the stronger material is, or stronger material will play against this kind of elastic deformation. So in some sense, you can understand that elastic modulus, which is responsible for the elastic behavior of the material, will be proportional to the stiffness of the atomic bonds, or in the mathematical way, so it will be proportional to the first derivatives at the point R equals R0 to these characteristics force to distance curves. And this you can see on this slide. Now, if you remember that force related to energy, again, through derivatives, specifically force equals to the derivatives of energy relative to the distance in the characteristic point, then we can easily find out that elastic modulus, which is proportional to the stiffness of the bond, will be proportional to the second derivatives of energy at points equals R equals to R0. It means that it will be proportional to the curvature of the corresponding of the characteristic, if you want, energy distance function, so at point R equals R0. So now you know that indeed elastic modulus is defined by the atomic level of structure, if you want, of material. More specifically, so if you do have the characteristic energy potential for this kind of material, so you have to take the second derivatives to this curve at equilibrium point, and elastic modulus will be proportional to these derivatives, second derivatives. So again, so typically, and that's also the case, the larger, the larger U0, we do have the higher second derivative, the higher curvature of the energy curves is typically observed. So we will have material with higher elastic modulus. So let's conclude, of course, so this case works not only for the ionic bonds, it works for any kind of bonds, including metallic bond. And on this screen, you can see so the elastic modulus for different metals, including aluminum, tungsten. You can see that it's can vary in the wide range from 100 to 400 gigapascal, and that actually is defined by the characteristic energy potential for this kind of elements. And to conclude this part, we can see, and we can compare now elastic modulus of different type of materials which we introduced in our previous lectures. And because, again, the difference of the energy potential, atomic potential for these elements, so the general conclusion can be made that elastic modulus for ceramics materials, when we do have so mostly ionic and covalent bonds, slightly higher than those for the metals. And of course, polymers, they do have the lowest elastic modulus. Okay, let us consider second example when we will talk about physical property. So, let's take such very well-known parameter or characteristic property of any material as melting point. So, you know in general, from your general life, that melting point is a temperature when the material somehow change its state. Now, let's say from solid state to liquid state. So if you think deeper, of course, this term is not so straightforward. And you have to know the concept of the crystal structure, the concept of the atomic vibration in each crystal structure, and so on and so far, in order to understand deeply this parameter. So, for example, so Lindemann suggested the criteria in order to describe this parameter. So everybody understands that in the crystal structure, so all atoms, they're in some sense vibrating on their position, having different temperatures. Increasing temperature, of course, leads to the increase of the amplitude and the frequency of this vibration. And so Lindemann suggested that if the vibration amplitude equals to some kind of critical length, which is related, of course, to the atomic, if you want, spacing of this material, then, so this may happen at temperature equals to the melting point. In this case, the crystal structure destroyed and material can be considered as melt. So let's again come back to the energy distance diagram for two different materials. You can see that the bonding energy for one material is larger than for another material, and you don't need here any additional, if you want, so explanations in order to understand. Then of course having higher U0, having higher energy bonding energy, it's much more difficult to make the crystal to vibrate with the higher frequency. So bottom line is, so without any additional so detailed analysis, we can conclude that if the atomic potential has the larger, deeper, if you want, the energy, then we do have material with the highest melting point. So now again we can see the direct relation of the atomic level of structure of the material, but now with the physical property such as melting point. And so the energy bonding, U0, is a critical parameter which defines this physical property. So again, so the melting point is larger if U0 or bonding energy is larger. So that's very nicely can be seen on this next screen, where we find the relation between the melting point and Young modulus. Remember, in the case of Young modulus, regardless of a relatively complicated relation between the potential energy curve or potential function and so the Young modulus, so we concluded that higher U0, higher bonding energy, higher Young modulus do we have, same relation we have for melting point. And so this screen very nicely demonstrates this idea that so materials, all elements with high melting point, they do have higher Young modulus. And this nice characteristic relation stands not only for elements, but for all known materials, including metals and alloys, ceramics, and even polymers. So again, so the next screen demonstrates this idea. So material with higher melting point typically does have the higher Young modulus. So finally, let's consider one more mechanical property, not so well known or very often discussed, but such parameter is coefficient of thermal expansion, CTE, if you wish, the parameter. So it's extremely important physical parameter of materials. The physics is relatively straightforward. You know that when, for example, you preheat your material, so typically it increases its length. And so the relative change of the length of your material, of the size of your material, is proportional, linearly proportional to the difference of energy. And coefficient of proportionality between the change of length and the change of temperature is so-called coefficient of thermal expansion. This coefficient of thermal expansion can be very different for different type of materials, as you can see on this screen. So it's extremely low for for ceramics, and it can be extremely high for polymers. So how we can make a conclusion about the relation of the coefficient of thermal expansion and atomic level of structure? Again, it's easy to see by the analysis of the energy distance diagram, which which are presented on this screen also for two different materials, where we do have the lower bonding energy and the higher bonding energy. So as we have discussed in the case of the elastic modulus, for higher bonding energy material with the lower value of bonding energy, so the type of the energy function, or the type of energy function, the view of energy function. So this energy function is much more wider than in the case of the strongest material. And so if it's so, then it's easy to understand why the coefficient of thermal expansion will be much more higher for the case of the weaker material than for the case of the stronger material. So indeed, we described before the parameter R0, which corresponds to the equilibrium state for our material, for the case when temperature equals to 0. Assume that temperature increases a little bit, and so please look on this screen. You will see that in this case, the atoms can increase or decrease the distance between them in the vicinity of R0, of course, so which allows the distance inside the energy function. And wider energy function, so for the larger distance, we can increase in the case of heating or decrease in the case of cooling the distance between two atoms, being not destroying the crystal structure. Of course, larger distance can be changed between these two atoms, the higher coefficient of thermal expansion we can expect. So it means that coefficient of thermal expansion in some sense proportional to the symmetry of the energy function, atomic energy function at point R equals R0. And that explains the whole case. Again, typically this function much more wider for the weaker bonds and much more narrow for the stronger bonds. That's why we do have the huge change of coefficient of thermal expansion for different type of materials. So, and that relation is very nicely demonstrated for different type of elements, so as a function of melting point. So now we have a vice versa relation. Material with the highest melting point, with the highest bonding energy, they do have the lowest coefficient of thermal expansion, and vice versa. So again, so this relation stands not only for the elements, but for all known up to date, almost all known up to date materials, and same so for metals, for ceramics, for polymers, and so on and so far. So materials with higher U0, with higher bonding energy, so they do have higher melting point and lower coefficient of thermal expansion. And from this standpoint, so of course ceramics, which do have the ionic and covalent bonds with the highest, if you want, the bonding energy, they do have the smallest coefficient of thermal expansion, while polymers, which do have relatively low atomic bonding inside the material, they have the largest coefficient of thermal expansion. And metals are standing somewhere in between. So by this, let me conclude the first main idea which we have discussed in this course, the relation between the atomic level of bonding and material properties. Now we know indeed that some type of mechanical property, more specifically we have discussed the elastic property of materials, as well as some type of physical properties such as melting point and coefficient of thermal expansion. All of them are defined by the atomic level of structure. So the next lecture will be devoted to the next level of structure, which is related to the crystal structure. And we will first of all find out what does it mean crystal structure and what kind of material so are defined by this level of structure. Thank you so much for your attention.